questions. Okay. All right, so as Vivek said, I'm going to talk about machine learning. We heard a little bit about statistical methodology yesterday, and we'll see how some of that dovetails with what I'm going to talk about today. What Vivek asked me to talk about specifically was how machine learning relates to the topic of the day, which is behavioral interventions. So Billy and I were supposed to talk and synchronize our presentations 2.5 months ago. We were never on the ground at the same time over the last 2.5 months, so that didn't happen, but I think everything will fit together fine. That was the lie for my truth and a lie that I missed on one day. Right. So where to start? So Billy just ran through in a very nice way a variety of different types of interventions. I'm just going to start with adaptive interventions, and we're going to look at how machine learning fits in with the sort of adaptive intervention landscape. Right? So this is going to be a recap of sort of what we just saw, and then we'll move forward. So when we're looking at the components of an adaptive intervention, like Billy just specified, there's a patient or a subject that we're interacting with. There's some environment that they're embedded in. So in many of these cases, that's just your natural free living environment. And there are interactions between the patient and the subject in the environment. There are some set of context variables or tailoring variables that we think are relevant for whatever it is that we're trying to do with the patient, right? And those might be things that could be captured by ecological momentary assessment, EMA, or labs, or maybe it's in clinical records, or maybe it's something that we get from sensor data, right? So lots of possible sources, social media, all kinds of options, right? So let's assume we have those context variables or tailoring variables. There's also going to be some collection of intervention components or treatment options or something like that, depending on the precise style of adaptive intervention that we're operating. And so our job is to figure out which of these intervention components to apply in this context of an adaptive intervention. And so as we just saw, what accomplishes that selection is the decision rule, right? So the decision rule knows what the set of intervention components are that could be selected, or intervention options at any point in time. And you're looking at what you should provide for who and when. Right? You can think about things that directly affect the subject, right? So we're going to prompt you to go for a walk, or we're going to prompt you to, eat a healthier meal. There's lots of different possible interventions that you might consider, different modalities. You can also think about interventions that modify the environment, right? So there are interventions where you can think about doing things like go into the workplace and replace your regular desk with a stand-up desk or something like that. Right? So we've made a modification to the built environment instead of an intervention sort of more directly involving a prompt or something like that to the patient. And then at the end of the day, there's outcomes that we're interested in. Right? So there's some set of outcomes. As Billy was just mentioning, there's two flavors of these, right? There's the short time scale proximal outcomes, and there's the longer time scale distal outcomes. So what I've got here, think of as like the proximal outcome, sort of what happens right now, but there's also this idea of the distal outcome, sort of the ultimate aim that we're interested in. Right. So in terms of an adaptive intervention, like we just saw, this is not the whole picture. This is just a snapshot of sort of one time point. Right? So what happens across time? What happens across time is we repeat this procedure, right? Selecting a particular intervention component to deliver, or maybe we don't deliver anything at all, at some number of time points, right? Like this. So the whole structure gets repeated over time. And again, the thing to remember is the whole process obviously has memory, right? So whatever we did yesterday or in the previous time point will affect what happens next. So what outcomes we had yesterday might have an impact on the outcomes we expect today or tomorrow. Yesterday's outcomes become today's context. The patient, obviously, we're changing things. We're intervening on the patient. The patient's going to change. Maybe their attitudes are changing. Something's happening if we're trying to do behavior modifications. Right? Other thing that's important to remember is things are not sort of just sort of one-time step back. Right? You can have long-range temporal influences. So, maybe what happened 2 days ago still has an impact, we hope, right? 5 days ago, a month ago. So the overall sort of dynamic picture of what's happening is fairly complicated, right? There's lots of stuff going on. There's the sort of 5 major components of the adaptive intervention, then replicated across time. And so in some sense, the problem of understanding how to optimize an adaptive intervention is sort of understanding this entire system. And how you get the information you need to make decisions in different places, what the decision points are, and so on. Right? So Billy just ran through this. Let me just recap. So there's these 5 components: the treatments or the intervention components, whatever the options are that you're selecting between. There's the context or the tailoring variables. there's the decision rule, the decision points, and the outcome measures. And there's all kinds of questions here, as Billy was just saying. Right? So some things that, that she touched on briefly, the idea of context. So the example that she was just showing for the MD2K smoking trial is around stress and smoking. Right? So you can assess stress using EMA. You can ask people to self-report. You can assess smoking behavior first lapse via EMA. Ask people when they lapsed. Right? The problem is the accuracy of the information that you get back when you're trying to look at relatively fine-grained timings. Like in the example of that study, you want to understand the relationship between stress and lapse. But if the sort of temporal resolution of your EMA is like once a day or 3 times a day or something like that, you have problems with recall bias. People are not going to remember exactly when it was that they had that first puff, for example. And so what would be nice is if we could replace that use of EMA with objective sensing, right? So we put sensors on people and we try to infer these context variables. Right? So how stressed are you, which is exactly what's going on in the study that Billy was describing. So how stressed are you? How much physical activity are we seeing in terms of steps and things like that? And then the same thing in terms of the outcomes. So in the smoking study, again, you can detect, or you can attempt to detect cigarette smoking as it happens, right, using sensors. So these two elements, inferring what the context is, right, based on sensing and other information, and inferring sort of the proximal outcomes, right, or detecting the proximal outcomes, are two important problems where there are other ways to solve these problems, but they have higher burden. Right? You can keep asking people, you can prompt them at higher intensities to get that information, but it would be nice if we could do this based on objective stuff. Right? So that's one place where machine learning can come in and help us. Decision rules is another one. Right? So in terms of these kinds of options, like what should the treatment components be, that relies on some of the ideas that Billy was describing. So if you want to figure out an initial set of intervention components, that needs to be a theory-driven process, where you have to have some idea of what the causal mechanisms are and how you can plausibly intervene to break the links. Right? But some of these components, in particular context, outcome measures, and then thinking about how to infer decision rules from data, are places where machine learning can help us out. Right? So I'm going to talk about context and outcomes primarily, and we'll look at sort of how that problem, that context inference problem that's used to infer stress, that's used to infer cigarette smoking, how does that work? What are the machine learning methods that are applied there, or more importantly, the machine learning methodology that's applied there to learn these computational models that perform these inferences for us. Right? I'll say a little bit about decision rule learning towards the end if we have time, but I'm going to mostly focus on the top one. And there's more than just these two things that machine learning can give us some leverage on in this space. In particular, one thing that Donna and Pedja and others and I've been working on for the last little while is sort of like a big model of this entire thing, using sort of ideas from probabilistic graphical models. So I'm not going to go into that because it's a work in progress, really. All right, so let's talk about context and outcomes. Okay, so here's the problem, right? We have people like Emory who can put together novel sensing devices to capture raw sensor data for us. And the question is, how do we take that data, again, from a single source, from multiple sources, and then turn it into these contexts and outcome measures that we care about, so that we can plug them into our interventions, right, and leverage them as context or use them as proximal outcomes. And this is where the machine learning comes in, right? So it's bridging the gap in this particular context between raw data and these higher level inferences that we'd like to have. Right? So you can imagine something where it's implausible, but you could imagine a scenario where you base your decision rule in your JEDI on raw sensor data. So it streams in at 150 hertz across multiple modalities, and your decision rule is, take a 15-minute block of this raw data and then decide what to do. Right? You'd have a hard time convincing anyone to actually field an intervention that worked in that way. Right? So it's nicer if we can think about inferring these intermediate context variables that are meaningful and that are interpretable to clinicians and to behaviorists as a sort of step in between this massive volume of raw data and the problems that we're trying to solve in terms of intervention design. Right? So the big data piece in terms of this work really occurs at the sensing level. So that data is extremely high volume, but it's extremely low information content. Right? So if you're looking at wrist movements or something like that to infer smoking or respiration chest band data, I'll show you some examples in a second. That data typically is sampled at anywhere, like I said, from 20 to 250 samples per second. But what you really want to know is, where did the smoking puffs occur? Where are the smoking sessions? How many steps did you have? Right? So this staged approach, another advantage of the staged approach, where you go from raw data to intermediate markers, these kinds of high-level context and outcomes, is that it provides you this data compression mechanism that squeezes the big sensor data down into these interpretable components, right? That you can then use. And hopefully, again, like with stress, hopefully what you're pulling out means what you think it means, right? That depends on how you design the data collection experiments. We'll come to that in a bit. Right? So we'll talk about this process of how do you get from here, right, the sensor data to over here. So what machine learning provides to us in this context, in fact, in all application contexts, is a set of tools for solving specific data analytic problems. So you can think of machine learning as a big toolbox, has lots of different methods, and similar to what happens in statistics. So what we're going to look at for this particular problem is a tool around detection. Right? So all of these problems, as Billy was just mentioning, we're looking at trying to understand, what's your physical activity level right now? So, or what physical activity are you performing? Are you walking? Are you sitting? Sort of postural activities. Are you smoking right now or not? Are you stressed or not? Or the degree to which you are stressed? Are you eating or not? Right. So what we're going to do is set this up as a detection problem. And the idea is we're going to have, so abstractly, we're going to have some kind of dynamical system. Think about the big picture that I showed you before, right? You've got the patient, environment, all kinds of things happening, changing over time. In this dynamical system, there's going to be some particular event that we're interested in, and at every time point, either that event is going to occur or not occur. Right? So you can modify this to look at levels, but for now we'll just stay with occur or not occur. Right? The detection problem is given some description of the state of that system. And again, that may be via sensor data, social media data, all kinds of other information that you can collect, the raw data, so some sort of raw description of the state of the system. We want to infer whether the event occurred or not at every time point. Right? So if we can solve this problem, then in a generic context, then it gives us this ability to say, at time 0, were you smoking? Yes or no? Were you, what was your physical activity? Were you running? Were you walking? Were you in conversation? Was there drug use? Was there stress? Whatever, right? So it's a generic tool that you can apply that will provide these context inferences. And what it relies on is you plugging in sort of these appropriate descriptions of the state and then matching it up with what are called labels or label data for whether the event occurred or not, right? So you need this paired input-output to do this. Pairs of what is your description of the state and then what actually happened. So did the event occur or not? Right? So that's what's called the detection problem, right? So you're trying to infer whether this thing happened or not based on some description. Let's see, so to make it a little bit more concrete, in the context of smoking, right? So if you look at Santosh Kumar's papers on smoking detection, there's use of respiration sensors, wristband sensors that are using accelerometry. So this is an example of what the respiration signal actually looks like during smoking. Who can tell me where a smoking puff happens on here? Let's count from left to right, 1, 2, 3, 4, 5, so on. What's the first place where smoking happens? Where a smoking puff? Donna, you putting up your hands? The third square, that's right. So the first one's right here, right? The next one's here. So there's the first one, there's the second one, there's a third one, there's a fourth one. Okay. So smoking puffs are characterized by deeper inhalation, deeper exhalation, and the entire respiration cycle, which is what the segmentation is here, is longer. Right? So everything else is not a smoking puff here. So if our problem is how do we learn a smoking puff detector, which is the basis of the smoking outcome measure that you can get, what we need to do is provide a mapping between these chunks of data corresponding to respiration cycles and these outcomes. So whether smoking puff occurred or not. Right? A further complication here is that because of the way the machine learning toolbox is set up, right, what it wants to receive as input is some fixed length description of the state of the system. So you can see here the way that we did this using variable size windows corresponding to respiration, they're all different sizes. So machine learning methods in general don't like inputs that are different sizes. It wants everything to be the same size. There's specific reasons for that, right? So a first part of this process, in terms of building a detector, is to take the raw data that you have and think about extracting from it what are called features, right? So in the featureization of this data, if you look at this, who can tell me what might be helpful for discriminating the pus from the non-pus here? A simple feature. I know some people in the room work on this specific work, so don't answer. Let's have somebody else. Suggestions. What do you see just visually looking at this between the red and the blue? The depressions? Okay. So one thing that you can see is that there's bigger amplitude range, right? So you can think of that as a stretch this way, right? So these ones that are non-smoking tend to be lower amplitude in terms of the maximum inhalation, maximum exhalation. These ones tend to be larger, right? So it's a deeper inhale and then a deeper exhale. It's also the case that they tend to have longer duration. So the respiration cycle lasts longer just because of the sort of biophysics. You're breathing in longer, you're breathing out longer, or deeper. The entire thing's going to be longer. Right? So we can think about taking this data and putting it into this two-dimensional feature space. Let's call one of the features of each of these pieces duration. We'll call the other one stretch. Right? So if we look at this point, that's pretty high stretch, pretty high duration. This one has lower duration, lower stretch. This one has, again, high duration, high stretch. This one's lower. Okay. So this is what we'll call our sort of feature space view of the data that we have. So we need to come up with some rules that will take the raw data and then turn it into these, again, we're already at the level of having something that's a little bit more interpretable than just the raw waveform data that we have. Right? And so what we're going to do is build a detection model in this feature space. Right? I'll tell you what that looks like sort of mathematically, and then we'll look at it geometrically as well, which is helpful. So if we have a whole bunch of data, we can do this for all the data that we have. We embed all the points in this feature space. Now we have a nice fixed length description. We have two numbers basically characterizing each of these chunks, the duration and the stretch. Right? So the detection problem that we're interested in will try to discriminate between the red points and the blue points in this space, right? By coming up with some function that maps every point in this space into a yes, no, was it smoking, was it not smoking result, right? So you can think about that something like this. So a detection function formally is going to be a function that will take a chunk of sensor data, we'll pull its, or whatever the data is, we'll pull its features out, and then we'll make a decision about what the label is associated with that piece. Right? So in this case, is it smoking or is it not smoking? So let's say this one corresponds to smoking. If you take that function and you apply it densely everywhere in the space, right? So let's say at every one of these grid points, we evaluate what the function is. We can make a map, right, of the function. It tells us where in the feature space we expect the output, right, the label to be positive, and where we expect it to be negative. So what this says is, if the duration and the stretch are high, then we're going to say it's smoking. If the duration and the stretch are comparatively low, we'll say it's not smoking. So you can think of what's happening is there's some function here, and we're trying to decide what it is, whatever this mapping is. Or you can think of it geometrically like this. We have some feature space, right? Our examples all are points in that space, and we're trying to learn a map in that space that will let us decide what are the positives and what are the negatives. So that's the goal, right? So where's the learning, right? So that's the description of the function itself. That's the object that we want, right? So the learning problem relies on the idea of being able to choose between different options here, right? So what we're going to say is a detection model is just a set of possible detection functions. Right? So if you know logistic regression, this is the decision function for logistic regression. Basically what you do is you take each of your features, you weight it by some weight, you add that set of weighted features together, and you compare it to some threshold. Right? So this is what the function does. So if this weight combination exceeds the threshold, we'll say yes, the event occurred. Otherwise, we'll say no, it didn't occur. Right? So that's a basic mathematical description of what's called a linear detection function. Okay. So if you're not happy with that, here it is geometrically. Right? So this is exactly what I just said. So this model, so the parameters here are we get to choose the weights in this model. Right? So if we have D features, we had 2 in the previous slide. If we have 2 features, we have 2 weights and a threshold. So there's 3 numbers we have to choose to specify our decision function within this family. Right? So it's parameterized by this little W indicating the coefficients. But it corresponds to this, right? So essentially what we're saying is the space of possible functions that we can get out of this model are all possible linear separators in this space with any offset and any sort of angle, right? So this model implies this geometry, right? You cannot get anything other than this out of this model, right? So it has to have this linear separation geometry in terms of what falls out. And so the detector learning problem is which of these ones is the best, right? We can get any separator in any position. It has to be linear. You can't get anything else. So amongst this set of all possible, uncountably, infinitely many possible maps, right? Which one is the best one? So formally, again, what we're going to do here in terms of the detector learning problem, we're going to try and solve this problem by collecting a sample of data, right? So we'll get sensor data in this case, in the smoking case. We'll get the outcomes, typically done in the lab. We'll come to that in a bit. So we know what you were doing. We know what the sensor data was at the same time. So we have the pairing. We'll call, again, the features we pull off of that X, we'll call the labels Y. And what we're going to try and do is specify some criteria that we can use to pick the best one of these maps, right? The best example of one of these functions. So mathematically, that looks something like this. What this is saying is, let's try to pick the set of parameters, the W's, that minimize the sum over the data sample that we have of the number of times that the true label, for instance, does not match the predicted label. Right? So we take the data, we plug it into our function, it gives us back an answer. What we're doing is counting up the mistakes. Right? So what this criteria says is pick the function, pick the map that gives you the minimal number of errors on the data that you collected. Right? So in the end, it's quite intuitive. Right? So if this is our data, right? If the red and blue dots are our data, this is a bad one. Right? It makes many errors. So it's saying, again, the shading indicates the map. So this part over here is saying it should be red, but there's blue stuff over here. That's not good. Here we have red examples, but we have blue as the prediction. This one's better. It only makes 2 mistakes. This one's even better. It makes no mistakes. Right? So that's the basic idea. In general, you can specify some criteria here. That's not just the loss. We heard yesterday, we talked about stats, about why you shouldn't trust accuracy, especially for class imbalance problems. There are other criteria that you can plug in that have a similar kind of feel. When the values are larger, it's worse. The values are smaller, it's better. So if you look at F1 or area under the ROC curve, some of the things that were mentioned yesterday, those are criteria that you might like to use here. It turns out that for specific reasons they're hard, but there are other proxies. Right? So there's a whole literature on different kinds of losses that are more robust to noise, things that might behave better in certain contexts. Right? But this whole area of detector learning relies on a formulation like this. Find the parameters that minimize some loss or discrepancy measure, right, over the examples. And we'll try to pick according to that. Okay? So let me show you an example of what this looks like, sort of, with a couple of different kinds of functions. So what we've got here, oops, sorry, just a sec. PowerPoint's always hesitant to show the demos. So I'm going to show you a live demo of what this looks like, right? So this is set up right now to use a linear model like the one that we were just looking at. And so the way it's going to work is we can click in this grid and we can put down our data points and it's going to tell us what the optimal function is, right? The way this is set up right now. Okay. And I'm going to use this to illustrate a couple of points, just to, things that you should have in mind when you're thinking about working with these kinds of models and this kind of data. Right? So here we go. This is going great already. Yep. Okay, let's try again. Go live demo. Okay, hold on. Let's start by rerunning all the code. Would you believe me if I told you this was working 2 seconds ago? Probably not, right? That's frustrating. Okay, let me come back to that. So let me mention just a couple of things, and we'll come back to the demo towards the end. Okay, so, all right, additional principles. So key thing, the key thing here in terms of the application of these methods is when you're defining the feature space, there are a couple of possible things that can happen. All right, so you have raw data, you're pulling features out of it. In terms of the performance of the methods, what was mentioned yesterday during the statistics talk, and we heard a couple of times the idea that like maybe it doesn't really matter what machine learning method you apply to your data, right? Maybe things are going to be sort of roughly the same. So in an example like the one I was showing here, where the data is basically well separated in the feature space, right? So the red points are over here, the blue points are over here. It's pretty easy to separate them into the two classes. In that case, it's true that it really doesn't matter what method you use, things are going to work okay, right? So if the data is well separated, in the sense, whatever method you throw at this is going to work pretty well. But when the data distribution starts to become more complicated, right? When you're in higher dimensional spaces, when you have weaker features that are not resulting in good separation like this, things become a little bit more nuanced, right? So one thing that can happen is that your features are just weak, and they can't do a good job of discriminating or indicating which of the two classes your examples belong to. So this is called the class overlap problem, right? So if we had just one feature, let's say this is our stretch feature for the smoking example, right? So if this light blue corresponds to the positive class, the dark one is the negative class, and the distribution of feature values contingent on the class strongly overlap like this, there's nothing that you can do based just on this feature that's going to help you classify accurately, right? You can't tell the positives from the negatives because you have some things, you have some examples over here that are going to be negative, some over here that are going to be positive, and you can't tell in that overlapping region sitting in here what's going on, right? So it just looks like noise. The example that we saw earlier looks like this one, where condition on the class, the examples are well separated, right? So there's not much overlap between the distributions. Right? So if, with respect to your features, you're in this situation, no method is going to perform well. Right? If you're in this situation, basically no matter what method you use, things are going to work okay. Right? The more subtle situation that occurs is where your data does have some separation, but not separation that's capturable by your model. Right? So remember, the model that we had here could only accomplish this linear separation between the examples because of the underlying mathematics. Right? So the underlying math implies some geometry. If your feature space, your examples in your feature space don't respect that underlying geometry, in this case, linear separability, there is nothing you can do. Your best model is not going to work well, even if your data has some structure. So let's imagine a data set where you have like an inner ring that corresponds to positive examples, and it's surrounded by another ring that corresponds to negative examples. Right? So it's possible to discriminate between those two classes. The distributions don't overlap, but they're not linearly separable. Right? And this is where appropriate selection of methods or equivalently appropriate sort of redefinitions of the feature space matter. Right? So you can misspecify the model that you're using here, and the results are going to be poor. And the task that you have then is to figure out whether fundamentally you're in this situation, right, where there's nothing that you can do, right? The features are sort of fundamentally overlapping, the distributions are fundamentally overlapping, or your model is just not the right one. Right? So we'll talk about this embedded in a broader context in a second. But those are some of the types of things that happen. This is where the idea of needing to choose between different models becomes very important, right? So again, it's not the case here that no matter what you do, no matter what model you choose, things are going to work equally well. Okay, so this is the basic detector learning problem in isolation, right? We have examples, someone gives them to us. Some are positive, some are negative. We're trying to figure out which is the best function from some model, right? The best detection function from among some set that we specify. That's often where machine learning people sort of like leave the problem at that sort of abstract level. But what we're talking about here is using machine learning in the context of behavioral intervention. So we have to embed the whole thing in a broader context. So this diagram is going to get scary quickly. So stay with me, all right? So what's going to happen is we're going to need to start by collecting data, right? So often if you talk to machine learning people, there are lots of machine learning people who never collect a single data instance in their whole life. Right? They download data, they're reusing data that was previously collected. They never sort of touch this data collection process. But this is where it starts, right? And especially in mobile health or in behavioral interventions, this is a very messy process, right? And very expensive. So you want to make sure that you're collecting the right information here so that whatever you're doing has some hope of working. Right? So we'll collect some data. Data cleaning is a big deal in mobile health. Right? The data's noisy, there's missing data, people forget to wear the sensors, the battery dies, whatever. Right? Data cleaning is a big deal. The feature extraction step is what I was just mentioning, what I was talking about. Right? So you have to pull out features. This problem is often called, so there's different ways to do this. The standard thing to do, or the easiest thing to do in some sense, is feature engineering. So that's leveraging domain knowledge to come up with good features like we did for stretch and duration for smoking. You look at the data, you try to figure out what's going to be helpful. You throw that in to the setup. Right? You also have to choose a model. Like I was just saying, you can have a linear model, you can have a nonlinear model. Current machine learning packages have tons and tons of different types of models that you can pick from. It's very easy to choose and evaluate many different things, right? And so like I just said, if the problem is easy to solve, it's not going to matter what you pick. Depending on the characteristics of your feature space, you can get leverage out of carefully thinking about what the right model class is, or testing different options. I'll say something about that in a second. So once you have all these components specified, right, you're going to learn your detection model. That means you take your cleaned, screened, feature extracted data, you pair it up with your labels that you collected, and you go through this detector learning process where you try to optimize your choice of model from your model class to get your individual detector. And then you're done, right? Okay, so what's next? Next, we have to evaluate, right? So we need to test this to see how well it's actually going to work. And these points were raised yesterday as well. The idea that you need some data for training, you need some data for testing or evaluation. Those can't be the same sets or you're going to bias your results, right? So again, you need to go through the same process. I mean, it's possible that you collect all the data at once and then you randomly partition it. You could go back out and collect another sample. We talked yesterday about why that might have issues. But you need a distinct set here. You run it through the same process. You take your learn detector, you apply it to get the detections. You take your collected labels and you evaluate. Right? So let's say we want to look at accuracy or some other metric, ROC, F1, whatever we're interested in, we evaluate. Right? If all our choices were perfect, we get good performance here, and we're happy. Right? Often what happens is you get into an iterative process where you're going to, you evaluate your performance, it's not great. Maybe it suggests that, you go back and look at the data, you realize, oh, this is, these features were not the best, or this model was not the best. Let's go back and change it, right? And so we can iterate a little bit here. What happens is the more you look at the outcome here to inform this, you're getting leakage of information from your test data into your overall model sort of selection procedure, right? So you have to watch out for that. In mHealth, though, that's somewhat mitigated by the idea that eventually there's going to be some kind of deployment that happens, right? So this is all, we'll talk about where these things happen and instantiate them specifically. But there's typically some additional phase where now we're down at the point where like Billy or Bonnie can grab this stuff, toss it into a just-in-time adaptive intervention or micro-randomized trial, and do this, run this process in real time, applying the detector for monitoring, for deciding on interventions, for other forms of analysis. Okay? So we're looking at least sort of 3 phases when we do this. I'm going to throw up this note of caution before I go on, and that is the more information, we heard this yesterday as well, the more information you can bring to this process, the less data you're going to need. Okay? This is often a problem in mobile health because of data scarcity, right? So getting labeled data is expensive, it's costly, it's burdensome on the participants. So it's tempting to sort of reuse the data you have for more and more different purposes. And this is the one that I was mentioning a second ago. So if you want your data to tell you what the right type of model is, you need to apply more advanced methodology than what I just described. Right? So this assumes that we chose the model and then we evaluated it. Right? If you want the data to tell you what the model is, machine learning has methods to do that. There are machine learning methods that will tell you what's the right model. Is it a linear model? Is it a nonlinear model? Which nonlinear model? Decision tree, random forest, or vector machine, something else? But this process, as complex as it is is not sufficient to do that. So we heard a little bit yesterday about methods called cross-validation or validation set methods. There are approaches that you can use to both estimate the performance of a method of a model and to choose amongst a set of different approaches simultaneously. So we're basically going to simultaneously pick the best kind of model amongst a collection of models and evaluate its generalization performance, right? But there's a whole bunch of extra machinery you have to toss in here at the point where you're learning the detectors, right? So this is a fairly common thing to see in application communities where people will evaluate, because it's so easy, you can easily like plug 10 different types of models in here. You can look at how well they perform down here. Then you say, my performance on this is the best I got out of any of the models that I checked, right? So I try 10 different things. Let's say one of them gets 70% accuracy, one gets 80, one gets 90, one gets 95. So I say, my performance on this predictive problem is 95% accuracy. Right? The problem is you're evaluating, you're sort of using the evaluation metric to pick between the models and then saying that the best of those is the performance of the overall procedure, and that is wrong. Right? That biases the performance estimates up. And the problem is that if you're embedded in this process and you're trying to figure out what's going to work and how well it will work and whether it's sufficiently accurate to actually deploy it, you can trick yourself into thinking you've got something that's great. And it turns out that because of a multiple comparison problem, effectively, the actual performance of the thing, the best performing model, is less than what you thought. So again, you can do proper data-driven model selection. It needs more data. You're giving the system less information. It will need more data to figure out what works best. And you have to use proper methodology. If you don't, you can trick yourself and things can go wrong. Okay, so that's an important note of caution. I want to further embed this in experiment design. So Billy was just talking about different kinds of trials. In terms of the kinds of experimental designs that people typically use in mobile health, there are several different things that you can do. So, for example, you can think about what is the within subject's performance, right, of a particular model. So what that means is when you're doing this whole process, how you choose the training data, the testing data, and then how you use it for evaluation impacts what it is that your performance results are telling you, right? So there isn't just an accuracy, right? The model just doesn't have some accuracy attached to it. It's all in the context of the experiment that you designed to assess that number. That experimental design sort of imbues that accuracy number with particular semantics. And depending on how you do this, you get different sort of conclusions. Right? So you can do this within subject design. What you do is take the training data, or for your training data, for every individual, let's say you take the first half of the data you collected, right? So let's say you collected data for 2 weeks. You take the first week and you build a model. You take the second week and you use it to evaluate, right? And so what that is doing is evaluating the ability of the model to generalize to new data from the same subject, right? That's the way you designed the experiment. That's what the generalization performance tells you for this design. This is useful. I mean, often if you're thinking about personalizing, this is the right kind of notion of generalization. But if you want to build something that doesn't need to be retrained for every person, which often occurs in the deployment context, then what you want to do is randomly partition your subjects and put some in train and some in test. Use all the data from your training subjects to estimate your model, then evaluate it on all the data from your test subjects. And what this does is evaluates the generalization performance from your training pool to your test pool. So it's telling you how well is this method going to work if we plug in data from new people we have never seen before, right? So you can use the same statistics to evaluate this and evaluate this, but they mean different things, right? Importantly, often if you have the data, this works better than this, right? Between subject variability is a large factor here. So building something within subject, if you have data, will give you better results than between subjects. So even if you want to say, the performance of this logistic regression model on this particular domain is 90% or 70%, those might both be true simultaneously, right? It's 90% if you do this, and it's 70% if you do this, which is not uncommon as a performance gap between these, right? Donna's favorite topic, right? What I'll call transfer design. So here the idea is, let's train and test with temporal splits for a particular individual, but let's not start from scratch for every person. Let's use some population level information to start the model off with some idea of what a population level average model would do, and then personalize it from there. So machine learning, that's called transfer learning. And this is what Donna refers to as the cold model, warm model, hot model scenario, right? She mentioned that in her talk. So this is often sort of, if you're going for within subjects, this is going to be more effective when you have small amounts of labeled data from your subjects that you're looking at personalizing to. Eventually, you should just forget the stuff from other people and just do the full within subjects. There's some tipping point between those two. Right? Okay. So that's sort of the full, or a fairly large spectrum in this space. Often we'd like to have within subject models. It's too costly to get that data in some cases, so you need to do sort of some version of one of these other things. But it's important to be cognizant of how you design the experiment so you can interpret the results that come out. Right? In terms of challenges, I already mentioned a bunch of these. So why is this problem hard, specifically in mobile health, or why can it be hard? Collecting accurate labeled data can be difficult and it can be costly. There's often a trade-off between ecological validity and the amount of data, the accuracy that you can get out, right? So a common problem related to that is what's called lab-to-field generalizability. And we heard about this yesterday as well. But the basic idea is, if you want highly accurate labeled data, bring people into your lab, right? And make them do things, smoke a cigarette, put their hand in a bucket of cold water and measure their stress response, right? You can video them. You can go back and look at the video. You can carefully annotate it down to like the millisecond level. What were they doing at every time point? You can build models in any of the modes that we put down here, right? Between subjects, within subjects. But that doesn't help us with the problem of all the data was collected in this lab setting, and that setting may not be at all representative of what's going on in the real world. So it's not uncommon to see, heavily scripted lab trials, even for like activities of daily living. There's a script and it's like, make a peanut butter sandwich, sit down in this chair, have a drink of water, watch the television, right? So the proportion of time you spend doing different things, nothing is reflective of what happens in the real world for any individual, right? So then when you take the models and you apply them in the real world, not surprisingly, you get this drop in performance, right? So there's a drop from within to between. There's typically a drop from lab to field as well. Right? Let me back up a second. Okay. The last thing I'll mention here is this between subject variability. I already mentioned a couple of times, but what this is sort of reflective of, again, in terms of big data, you might think that you collected data, like Billy said, from 400 people, right? You're trying to evaluate some intervention. That sounds like a lot. But if you have these substantial between subjects effects at the level of understanding when is smoking happening or what does stress look like for people, this kind of like big cross-sectional data, you have lots and lots of data from different people, doesn't necessarily help, right? It may be that you really need big longitudinal data from the same person. And this is what Deborah Essen calls the N equals me scenario, right? It's like everybody's different. Having data from 1,000 people is not going to be as helpful as having a whole bunch of data from the same person. So that's something else that comes in here and makes things a little bit trickier as well. And these are, again, the reason I point these out is that these are things that don't often happen in other areas of machine learning. Right? They're somewhat specific to mobile health, and there's specific challenges for these applications. I mean, this one in particular for obtaining labels, there's an interesting problem that has to do with how temporally precise are the event labels that you can collect. Right? So if you're looking at smoking puffs, that event only lasts like 1 second, right? So if you're having someone observe a subject smoking and they click a button on a smartphone every time the subject takes a smoking puff, which is how the lab studies worked here, and you're off by 1 second, your labels are all wrong, right? So after the smoking puff comes a non-puff, right, for the most part. So if you're off by 1 second every time, you labeled all the non-puffs, right? And all the puffs got missed. And now you try to train a model, it's going to be horrible, right? So there are issues around, again, the sort of like precision that's needed to learn models that don't occur in certain other areas. Okay. I'm going to skip over the decision rule piece here. I'll just say a couple things about it. So machine learning can also be used for inferring decision rules. This ties in with micro-randomized trials and ties in with an idea of a particular form of learning called reinforcement learning. What it solves is the problem of, this problem of, in a intervention optimization context, someone asks the question, how do we optimize for the end-to-end performance in a trial, right? So what Billy described that MRTs can do is optimize performance with respect to individual proximal outcomes, time point by time point. But if what you care about is what happens at the end, you need a slightly different sort of learning setup that's able to optimize for long-term reward or long-term outcomes over multiple time points. And so that's what this, let me skip through this, that's what this idea of reinforcement learning does. And it's useful in this particular context of optimizing end-to-end intervention performance. So I won't say more about it. The keyword is there. Some people are using this to do end-to-end optimization. I think Pedge is doing this in some of his work now. It's sort of the right tool, and it complements some of the other things that we've talked about. Right? Okay. So there's, like I said off the top, there's all kinds of other stuff that machine learning can do here. The sensors to outcomes is one of the more pertinent right now, just because that you have these big data problems of huge sensor data volumes down to smaller numbers of contexts and outcomes that you're interested in. But there's all kinds of other stuff. One of the groups is working on computational phenotyping, which is a clustering problem. That's another area of learning. Dimensionality reduction provides methods that you can use to automatically infer good features from data. Classification is what we've been talking about, detection problems, discrimination. There are also methods for regression that are different, somewhat than the ones in statistics that have different properties. There's all kinds of stuff here. So, conclusions. There's a lot of stuff in the machine learning toolkit. We went a deep dive in one of them. As an ML user, you have to make sure that you design valid ML experiments. That's the most important piece, so that you can correctly assess the generalization performance of the methods you're using. If you do that, you won't trick yourself into thinking that you have something that works better than it actually does. That's the most important thing, right? So if you get some result, if you correctly infer that what you did was poor, that's safer than incorrectly assuming what you did was correct, right? Then you realize it's not good. Go talk to a machine learning expert that can help you try different methods, right? And in particular, keep in mind that mHealth has a number of particular problems. They don't exist in other areas. You need to watch out for them. This between subjects variability, different kinds of problems with labeled data collection. We are working through the MD2K Center on generalizable solutions to some of these problems, and sort of stay tuned. That's also a work in progress. All right, thank you.
Perfect. Questions? Everything you want to know about ML?
Yep.
So the flow chart that you showed us on the
Yep.
So there are many of those. I want to know what is how do we know when the definition is defined? First question. Second question is
we will have to take only one. We are running behind.
Let's see. Okay, so the question is, I mean, the fundamental loop here is this sort of model refinement loop, which is an important part of modeling, right? So it's very hard to get your modeling correct the first time you go around these loops, right? Let's look at this. And so it's almost inevitable that you do some amount of this. That question of like when to stop, right? The stopping problem is an important one. And again, that needs to be decided in the context of what the end-to-end application is, right? So if you think about F1 performance that we were talking about yesterday, it breaks down into sensitivity and specificity, right? If you're okay having an application where you might have a certain false positive rate, right? So if you're thinking about triggering an intervention on stress, and the false positive rate for inferring stress is 1 event per hour, right? And you're going to trigger an intervention based on that, that could be very bad for your intervention over the long term. Okay, so even one false positive detection per hour, which then triggers the intervention to jump in and say, do you need to do this breathing app or something, right? That could cause long-term disengagement in the intervention, right? Similarly, if you think about it the other way around, think about the false positive rates. If they're too high, again, you're going to be missing things occurring. And so when you evaluate the end-to-end effectiveness of a JITI, as Billy was describing, the entire effectiveness is moderated by the accuracy of the machine learning methods that are producing context and proximal outcomes. Okay, so it could be the case that your design is awesome in terms of the trial. You have just the right intervention components. But if your machine learning pieces are feeding you information that says, now you're stressed, this was smoking, this was physical activity, and it's all wrong, all the contexts are wrong, the decisions are random, you wash out the effect of the trial. Right? So the importance of getting models that have some certain performance characteristics when you can stop or when you should stop is dependent on what you're trying to do and what your tolerance is for these sort of false positive and false negative detections in the context of the intervention that you're trying to perform. So that was a great question. Thank you.
Great. So we're running a little behind. Apologize, we're into your break. Grab a snack and the teams will meet in your room at 11:30. So one of the requests, there are 4 of you who have not yet finished yesterday's evaluations. If you could complete that so they can close it out by noon, that would be terrific. At noon, we have a treat for you, just to keep you incentivized. Show up there in the exploration room at about 10 to 12 and begin on your lunch and have another great afternoon. So onwards with the day, Carpe Diem. Okay, thank you very much. Thank you.